All right, explore number 2. Using vectors and scalars to describe motion. I'll go ahead and draw the lines. Make sure you put the date. The essential question for this explore is in green. How many problems involving two-dimensional vectors and their components can be solved? How may problems be solved? Okay, so I'm going to write that out. How may problems involving two-dimensional vectors and their components be solved? Question mark. Okay. Okay, so we're not talking about three-dimensional problems, say X, Y, and Z axis. We're talking about your standard two-dimensional problem, like we might do on a piece of paper, X and Y axis, right? So let's just go ahead and write down what you know, okay? Or you think. Okay, get your brain thinking, get it primed, right? And hopefully you paused and wrote that down. As we take a look at this explorer, we can see that we've got manipulating vectors right here. Got some information on connecting them, adding them, subtracting them. Got okay, and looks like we got some manipulating vector sample problems. A lot of sample problems there. Looks like we're going to talk to you a little bit about trigonometry. Doesn't that sound exciting? And then we have a practice problem there. Okay. All right. Well, let's go ahead and clear the screen here. And Roman numeral 1. Manipulating vectors. Okay. Let's go ahead and just click on this term here. Vectors. What exactly is a vector? A quantity with components of both magnitude and direction. You remember that from your last explore, right? Versus a scalar, which only had magnitude, right? Vector quantities measure both the magnitude and the direction, okay? The first step in solving problems that involve vector quantities is usually to make a diagram. Make a diagram. Okay, and I don't know why all of a sudden this thing switches. Like now it only works with my finger, but I'll try to keep that straight. Sometimes the arrows representing vectors are drawn so that the lengths are proportional to the magnitude, right? A scale is chosen such that the vectors can be drawn with the lengths directly proportional to their magnitudes. Okay. So I guess we got some rules. Vectors are drawn proportionally to their magnitude. Okay. Diagrams are helpful. Diagrams are useful. Okay. And here you can see an example. You know that this is a vector force because you've got this V with an arrow over it, right? Remember that that was one way you can communicate that this is a vector quantity. And if you notice here, the 10 meters per second was half as long as the 20 meter per second. Okay, so the magnitude is represented by the length of the arrows. Okay. Okay. Clear the screen there. So far, nothing new. You guys know this. Vectors can be combined when they represent the same units and they act on the same object. Okay, this was probably, we talked about this, but this is worth reminding ourselves. Vectors can be combined when they represent the same units and are acting on the same object and are acting on the same object. Okay. And in this case, you can add them, you can subtract them. What is new here is the paragraph underneath. Let's go ahead and just slide this up here. They talk about this head to tail method. Highlight clicks. Okay, I'm not really sure about that. The head to tail method, right? So let's go ahead and over here, I'm just going to put down letter D. Adding, we'll just say head to tail method, okay? Head to tail method. In this one here, example, you could take vector number 1, and maybe this is going to be 2 newtons, and you can add that to vector 2, which is 4 newtons. And what they're showing here is that this would be equivalent to you saying that they're combined, if you were to add them up, is equal to 6 newtons, right? Okay. In this case here, the head are the arrows. These are the heads. the heads of the arrows, and the tails would be this portion right here. Okay, these are the tails of the vector arrows, right? Okay, so the purpose of me doing these notes with you, of course, is we're just trying to tear this apart and clarify things, okay? Okay. You could call this a resultant vector if you wanted to. This is a resultant vector. Okay, all right. Okay, so just kind of moving along here. So far, hopefully all this stuff is making sense. You've seen these kinds of examples. We've worked with these on the board. If they're acting on the same object, they're moving in opposite directions, then this would be a subtraction problem. And you could draw a resultant a vector right here. This could be our resultant vector, right? That could be the resultant vector. These two forces are acting on the 20 kilogram box, and they're opposite directions, so they're being subtracted. Okay, so let's just make some points here. The forces act on the same object, right? They're acting on this object, right? They're in opposite directions. Opposite directions. Therefore, this would be subtracting, subtract, right? Therefore, you would subtract these. And this is equivalent to, it's equal to you saying this, just a 15 Newton force to the right, because isn't that what that is? 20, a positive 20 added to a negative 5. What is 20? A positive 20, right? Because this is a positive direction. This is the positive direction, and this is the negative direction over here. A plus 20 plus a negative 5. That's the same thing as saying 20 minus 5, right? That would equal 15. Okay, all right. Okay, so let's see here. Let's continue. Okay. Oops, clear the screen here. And let's just move this up here. Okay, drawing a diagram of the forces acting on an object can be very useful in analyzing motion problems. Okay, we like this word here, the concept of free body diagrams. Has more information about showing force vectors. So it sounds like there's maybe a chapter further down the road that talks just about free body diagrams. Okay, but you know, the box with the arrows pulling or pushing on it, that was a free body diagram. They're useful. This is a free body diagram. These are free body diagrams. Okay, so let's go ahead and just write that down over here, okay? Letter E, draw free body diagrams to conceptualize and to analyze. Yes, I said the word analyze, right? So we can do more with these drawings, and that's what we're trying to set you up for. When two-dimensional vectors of any type are to be added, okay, I'm right over here right now, they might not act in the same or exactly opposite directions. In this case, they can be combined using a diagram of a parallelogram. Okay, so here we're starting to go a little bit deeper. Parallelograms. Parallelograms. You know, you may say that a box is a parallelogram. You may say that a rectangle is a parallelogram. And parallelograms can also be at angles. These are all examples of parallelograms. The point is that the sides, this side is congruent with this side, and this side is congruent with this side. That means that they're the same length. Okay, that's what we're talking about. These are examples. Example, okay, of parallelograms, right? Now, let's clear our screen over here and let's move on up. The illustration 4. Here we are. It says the two vectors are drawn as adjacent sides of a parallelogram with their lengths proportional to their magnitudes. Sides added parallel to these vectors complete the parallelogram shape. Okay. And then finally, drawing a diagonal of the parallelogram that starts at the base of the two original vectors gives the resultant vector. Its length gives the combined vector's magnitude, and its direction gives a combined direction. Okay, so you may have, for example, let's draw this as another example. Okay, if this was example 1, let's go ahead and write down example number 2. And let's say that we have a force. Okay, we'll say that we have force number 1. And we're going to say this is F of 1. Okay, and we're going to say that's a vector quantity. And you have another we'll say this is our F of 2, and it also is a vector, right? So what they did was they said, well, let's go ahead and we'll take this blue one, and we're going to go from the top here, and we're going to draw that same arrow. This is where probably it would be helpful to actually have a ruler or something so that you were actually measuring that exactly the same, right? And then I'd say, okay, take this red one, and this is also going to be my thing is trying to correct it, autocorrect it or something. That was weird. I didn't want that. Let's see if I can undo that. I'll try that again with, hopefully it won't do that. Okay, so there we go. And now what I'm going to do is I'm going to draw my resultant. Okay, so maybe what I should have done too is I should have done this. Maybe I should have just kind of drawn these little hash marks so you knew that these were right, just so you know that those were the second arrows. And now I'm going to draw my resultant. This is my resultant. And this is a combination of the F1 and the F2, okay? This is, notice that it's longer than either F1 or F2. Also, note the direction. Okay, so this can allow you to predict the direction of combining F1 and F2, and it can also allow you, so this allows us to analyze or predict the result of combining vectors. Because that's what we just did, right? We just combined them and we were able to calculate our result, okay? So, and they would have called this your F resultant, right? Vector. Okay, well, that's that. Take a moment just to think about that, chew on that a little bit. And let's just keep on moving. In the special case of the two vectors being at right angles to each other, the Pythagorean theorem can be used to find the length of the resultant vector. Okay. In the special case of the two vectors being at right angles. Okay. So, example 3, I guess. What if you had your f of 1 was like this, and your f of 2 was like this? Right? So what we're talking about here is we're talking about these are at right angles to each other, 90 degrees. What we call a right angle. Then what you can do is you can go ahead and use the Pythagorean theorem. And the Pythagorean, there it goes again. I didn't want that to happen. Let me see if I can get rid of that somehow. So the Pythagorean theorem, you can use the Pythagorean theorem when your vectors form 90-degree angles. And the Pythagorean theorem, if you recall, was this. It's a squared plus b squared equals c squared. And this would be where you might say that this was your A side, and you might say that this was your B side, and this is your C side here, okay? And you could use this theorem to calculate any of those, okay? All right, lots to think about. Moving on. If there are more than two vectors to add, draw the vectors in a chain. Okay, linking them head to tail in sequence. Okay, so head to tail. linked to head to tail, linked to head to tail, linked to head to tail. Okay. And notice your resultant is going to start from the tail of the first and the head of the last. Okay. This resultant drawn from the first tail to the last head. Okay. And this is for when you have a sequence. Okay. A sequence. So let's just write this as letter G. When dealing with a um, with more than two vectors, draw them as a chain. Draw them as a chain. Okay. And we just explained that, right? But we could go ahead and example. We could say they had force 1, force 2, force 3, force 4, and your resultant could be this. This could be your resultant. F resultant. Okay. Would be that one right there. Okay. All right. I think we're almost finished here. So they kind of go through here and they show you different ways to break these down. The point is that you always try to resolve it in the simplest way possible. Okay, keep it simple, stupid is the expression. Don't make it any harder than you have to. Okay. And if you move down here, in physics, when a vector quantity is in two dimensions, it is often useful to break it into two components that are at right angles. Why? Because you can use the Pythagorean theorem, right? This results in a parallelogram that is a rectangle. Again, if you can keep things as simple as possible, you're going to make your life easy. The math is going to be easy. Often the alignment of component vectors is chosen in a way that is convenient for analysis. That's an important point there. For example, one component might be parallel to the angled surface of an inclined plane. The most common choice is to choose components so that they're parallel to the horizontal x and vertical y axis. Okay, so as you are trying to make decisions about how to diagram, do your free body diagrams, you want to try to make it as easy as possible for your analysis. Okay, so maybe that's what we're going to write down here. Okay, this will be letter H. Always draw free body diagrams or your vectors in such a way to make analysis easy, okay? i.e., right angles. Well, right angles on parallelogram, or a line along x and y axes, plural, right? Now, here's an important point here. Instead of a drawing, trigonometry can be used to determine the components of a vector as well. Okay, so let's go ahead and say letter. I'm going to give us a little space here, okay? But we're going to say this is I. Trigonometry can also be used to determine components. Okay, so I guess if we were to, before we move on to the trigonometry, if we were to come back up to this problem here, letter H, if you have a i.e., we're talking H, if we have a vector that is going this direction, you may be trying to decide how you want to break this apart. Do you want to break it apart like this? Say, well, here I can go that way, and I can go that way, and I can go like this and like this. Well, you could do that, but wouldn't it be easier if you took that arrow and you said, let me just go ahead and make this actually come straight up. This one straight down. And then my black one goes straight across. And my black one goes straight across. See here? This is the better choice. Okay? This is the better diagram. Why? Because you have been able to create your 90 degrees. This is going to make it a lot easier for analysis. Okay? Better diagram, easier to analyze. Okay, so whenever you have a choice on how to represent your forces into component parts, try to make them as easy as possible. Okay, so let's get into this whole trigonometry thing, okay? Let's just get done with this because there's a lot that we're talking about here. All right, so they give us an example. You've got this force of 5 newtons, and it is acting at an angle of 37 degrees from the x-axis, from horizontal. Okay. Could you figure out F1 and F2 using trigonometry? Okay. So let's just go ahead and draw this here. We have example here. We've got a box, right? And we've got 5 Newton force, and it is operating at an angle, and this theta, that's what they often use to represent your angle. Theta is equal to 37 degrees. Okay. So you're going to get into some rules here that I guess we should talk about. You have sine of theta, which is going to be your opposite side over your hypotenuse. You have your cosine of theta, which is going to be your adjacent angle. Okay, opposite angle, or opposite side, I'm sorry. Opposite side, adjacent side over your hypotenuse. We're talking triangles right now. And you also have a tangent one, but I think this will be fine for right now. Okay. So the question here is, could you figure out, say, this vector? And could you, in fact, really figure out, say, this one? Could that be done? And the answer is yes, because you could go ahead and just draw this kind of parallel thing over here. This would be your, if this is your theta is 37 degrees, opposite to that, this is your opposite side. This is your adjacent side, okay? And this is your hypotenuse, okay? Okay, we're talking, everything is in reference to theta. Theta is the angle, okay? So if we take a look here, and they do exactly this sort of thing here, read through the problem, read through the solution. But what they do is they say, okay, in this particular example, what was theta? Theta, the angle was 37 degrees. So if I can go ahead and expand that just a bit there so you can see here. So we could say our formula, right? We're using this formula. We're going to use this formula right here. So we'd say the sine of 37 degrees is equal to, what was the opposite? Remember that this was, this might have been our f of 1, right? And this was our f of 2. So the sine of theta, what was this opposite one is f of 1. It's the opposite vector, which we don't know, over the hypotenuse. And the hypotenuse was 5 newtons, right? 5 newtons right there. Okay, this F1 over here, remember, if this is F1, then this also is F1, right? Because it's a parallelogram, those sides are going to be the same. So, well, you've been learning how to rearrange formulas. So we want to solve for f of 1. So you need to get f of 1 all by itself. How do we get f of 1 all by itself? I'm going to write this out on the side here. Get f of 1 by itself. Okay, so we're going to multiply this side times 5 over n. 5 divided by 5, that cancels out. What you do to one side, you do to the other. So 5 newtons times the sine of 37 is going to give you your f of 1. So then what you do is you'd get on your calculator and you would just say 5 times the sine of 37. Okay, so 5 times the sine of 37 degrees, okay? You just multiply that together. And I don't have my calculator handy there, but you would get an amount of 3 newtons. And so you would not have to use a ruler. You could just simply use some trigonometry and you could actually figure out these resultant angles, okay? We'll probably try to work some of this stuff in the class as well, just so you can have some practice with calculations using the calculators, okay? But I encourage you to pull out the Desmos calculator and look for that little button that says sine, and then just hit sine and put 37. You do have to make sure your calculator is in degrees and not radians. And we can talk about that in class as well, okay? But that would affect your answer. Alrighty, I hope that helps. Oh, you know what I want you guys to do? Write yourself a summary sentence now, okay? But I know you're glad to be finished with this lecture. So let's just write that down, okay? Summary sentences or paragraph. All right, talk to you later. Bye-bye.